Hey friends, welcome back to the channel and to the 7th episode of the research paper summary. Today I'll be covering the paper, A Robust and Domain Adaptive Approach for Low Resource Name Entity Recognition. This is a very good and easy paper to read, but more importantly, this paper can easily be replicated and applied to whatever domains you're currently working on. In this video, I will first cover the context and contribution of this paper. I will then dive straight into the proposed approach RDANER, which stands for Robust and Domain Adaptive for Low Resource Name Entity Recognition. I will then finish up this video by sharing the experimental results and analysis. I hope you find this video useful. Let's get to it. If you're new here, my name is Ryan. I'm a first year PhD student based in London, and on this channel we explore and share actionable insights on different topics in AI research, entrepreneurship and lifestyle design, encouraging us to take more actions and live a happier and more intentional life. If these topics sound interesting to you, consider subscribing. If you haven't noticed this already, the common theme in name entity recognition is that whenever you try to apply it to a less popular domain or language, you are faced with limited data to train your neural models. And so many recent work has been proposing different methods to tackle this problem, which includes using external resources such as external entity lists or knowledge bases. In general, most recent work can be categorized into two groups. First, the learning-based methods. This include transfer learning, multitask learning, and distance supervision learning. The second is domain-specific pre-training methods. This is a very popular approach of pre-training general domain language models using a huge amount of unlabeled datasets. Both methods are quite effective for low-resource NER, but each method has its own limitation. The learning-based methods are time-consuming and expensive to implement, whereas the domain-specific pre-training methods are more computationally expensive. And so we need to come up with a much more feasible and robust approach for low-resource NER. This paper proposed RDANER, which stands for Robust and Domain Adaptive Approach for Low-Resource NER, that uses cheap and easily available resources. The approach has two steps, which are as follows. The first step is transformer-based language model fine-tuning. Here is where we fine-tune a general domain pre-trained language model using in-domain data to make it fit into our target domain. Here, general domain language model and unlabeled dataset are easy to obtain. The second step is bootstrapping. Here we start with an initial NER model trained using a small fully annotated seed data. We will use the initial trained NER to predict the unannotated dataset, which we will then use the new dataset to retrain our model further until it converges. I will cover this process in more details in the next section of the video. Now we will dive deeper into the RDANER approach. In order to apply the RDANER approach to low-resource NER, we need to have access to the following four things. First, we need access to a small fully annotated seed dataset. Secondly, we need access to a small in-domain corpus, which allows us to generate weakly annotated data. Thirdly, we need a general domain pre-training language model. And lastly, we need a large-scale in-domain dataset. Here you can see the architecture of the RDANER approach. As mentioned before, there are two stages. The first stage requires you to fine-tune language model. Here, our general domain language model is BERT and is fine-tuned using domain corpus. In the paper, we focus on two challenging domains, computer science and biomedical, hence BERT-CS and BERT-Bio. The domain corpus for computer science consists of 127,000 research papers, whereas the biomedical corpus contains 200,000 abstracts from PubMed. The second stage is bootstrapping. Bootstrapping firstly involves training an initial NER model using the small fully annotated seed dataset, which is represented in the green rectangle. Here you can see that the fine-tuned BERT from step 1 is our word encoder, and we have a linear chain CRF after a softmax layer. The next step of bootstrapping is an iterative process. Once you have trained the initial NER model, you will use it to assign labels on the small in-domain dataset to get our weakly annotated dataset. Combine the weakly annotated dataset with our initial small fully annotated seed dataset and train our NER model using it. The second round of training and all the rounds moving forward is a bit different than the initial round because we set a hyperparameter threshold to filter tags with low probabilities outputted by the softmax layer. We will continuously train our NER model with the augmented dataset until the model has achieved an acceptable accuracy level, or whenever we finish K rounds of training. Let's now move on to the experiments and results. The paper conducted experiments on 3 benchmark datasets covering the computer science and biomedical domain. Here are the datasets. The first one is the computer science dataset, which has 6 different types of entities. The second 2 datasets are both biomedical datasets, and they have 2 and 1 entity types respectively. The percentage seed of the training set here is to simulate the limited annotated data setting. Let's now talk about the results. Here I will go over the effectiveness of language modeling fine-tuning, the performance of bootstrapping, the huge difference in computational resources needed, and lastly the comparison of state-of-the-art learning-based methods. First we will talk about the effectiveness of language modeling fine-tuning. As you can see in this table, language modeling fine-tuning consistently outperformed BERT based on all 3 datasets, showing that language modeling fine-tuning is effective and domain adaptive. One observation is that the performance gap actually decreases when training data increases for all 3 datasets. This showcased language modeling fine-tuning actually works better on less training data. The second is to evaluate the performance of bootstrapping. The combination of bootstrapping and language modeling fine-tuning results in RDANER. As you can see here, RDANER outperformed all results in all 3 datasets. These showcase the additional benefits of the bootstrapping methods. Bootstrapping was able to always further improve the accuracy of NER models. In this table, it showcased the performance of the iterative bootstrapping process using just 10% of the training data. As you can see through each iteration, the results clearly show that bootstrapping contributed to the performance increase. The next figure here showcases how the different level of theta, the threshold level, is affecting the F1 score. Here, the 2 general observations are, first, increasing the threshold seems to result in higher precision, and lowering the threshold seems to result in higher recalls. Secondly, we found that recall tends to have a high impact on F1 score under low resource settings, and this is shown by a smaller optimal threshold. The third analysis that I really want to talk about is the comparison with domain-specific pre-training language model. Both Cyber and BioBird perform really well in their respective domains. However, both are expensive to train, as shown here. Although RDANER wasn't able to outperform both Cyber and BioBird, it was able to achieve a very competitive results to them, with significantly less data and computational resources. RDANER models only use 2.5 to 3.5 hours of compute power, versus Cyber and BioBird, which uses 42 days to 254 days. Lastly, I want to show that the RDANER models was able to achieve state-of-the-art results in the 2 biomedical datasets using full training data. It was also able to achieve the second best performance in the computer science dataset, showcasing the domain adaptiveness of the RDANER models. And that's it for today's video. I hope you find this video useful. If you like this video, be sure to subscribe, as I'll be covering more research paper summary videos in the future. In the meantime, feel free to check out other videos on my channel. Thank you for watching. I'll see you guys in my next video.